Hello class and welcome back to Chemistry in the Physical Setting. This is Unit 3, Periodic Table, and this is Lesson 1, Arrangement of the Periodic Table. And so the major understanding for this lesson is that the placement or location of an element on the periodic table gives an indication of the physical and chemical properties of the element, and the elements on the periodic table are arranged in order of increasing atomic number. So the first periodic table is developed by Dmitry Mendeleev, who is a Russian chemist, and he observed that when elements were arranged in order of increasing atomic mass, similar chemical properties appeared at regular intervals. And so his periodic table was, he placed the elements according to increasing atomic mass, and every time there were analogous physical properties, those elements were then placed in the same vertical column. So for instance, hydrogen had properties very similar to lithium, so they were placed in the same vertical column. Then he continued to arrange the elements according to increasing atomic mass until he found that sodium had similar properties to hydrogen and lithium, so it was placed in the same row, same vertical column. So elements in the same vertical column have similar chemical properties. There were some problems associated with Mendeleev's periodic table. The first being that there were empty spaces in Mendeleev's table. So Mendeleev had to leave empty spaces in his table in order for the elements to be placed in their proper vertical columns. So titanium reacts very similarly to silicon and zirconium and carbon. So space had to be left between calcium and titanium so it would be placed in the column with the elements with similar chemical and physical properties. Mendeleev believed that these empty spaces represented undiscovered elements and predicted their physical and chemical properties. And he was correct. There were actually undiscovered elements that belonged in these spaces, and some of them were even discovered during Mendeleev's own lifetime. There was also the tellurium and iodine exception. Tellurium and iodine, when arranged according to their atomic mass, do not align up vertically with the elements that have analogous physical and chemical properties. So if you look at tellurium, tellurium's atomic mass is actually greater than iodine's. Tellurium has an atomic mass of 128, iodine has a mass of 127. Yet iodine reacts similarly to elements in row 7. So fluorine, chlorine, bromine, and iodine. And tellurium reacted similarly to oxygen, sulfur, chromium, selenium, these elements. Okay, so Mendeleev had to switch these elements' placements on the periodic table so that his periodic table made sense. And because of this, Mendeleev's table wasn't taken too seriously due to the fact that there were these empty spaces, and also due to the fact that when arranging elements in order of increasing atomic mass, you have this exception between tellurium and iodine. So again, tellurium has an atomic mass of 128 and iodine has a mass of 127. So they should technically be switched, although they react similarly to the elements in the columns in which they are placed. And so that was the exception to Mendeleev's system for organizing the elements on the periodic table. So the modern periodic table, the discovery of subatomic particles contained with the atom allowed for a revision of the periodic table. And specifically the discovery of the proton. So the modern periodic table is arranged in order of increasing atomic number, or in order of increasing number of protons contained within the nucleus. And so this is the modern periodic table, along with many more elements that Mendeleev did not know of, including the noble gases, due to their the fact that they're very unreactive. They're very difficult to witness. So they went undiscovered during Mendeleev's lifetime. When arranged in order of increasing atomic number, the tellurium and iodine exception disappears. So if we look at tellurium and iodine again, now that they're arranged according to the number of protons in the nucleus, now they're arranged correctly, where tellurium has 52 protons and iodine has 53 protons. So now, since the elements are arranged according to increasing atomic number, that exception, it's no longer an exception. So some information that's available to us on the periodic table. Atomic number represents the number of protons contained within the nucleus. So an atom with 3 protons will have an atomic number of 3. The next is the elemental symbol, which is either a 2 or 1 letter symbol that represents an element. The element with atomic number 3 or 3 protons contained within the nucleus has an elemental symbol of Li, and it's the element lithium. The rule here is that the first letter is always capitalized and the second letter is always lowercase when writing the elemental symbol. The next is the electron configuration, and this represents the quantity and location of electrons within an atom of an element. So the electron configuration of lithium is 2-1, and so what this is telling us is that in the first energy level there are 2 electrons, one here and one here, and then in the second energy level there is 1 electron. And since second energy level for lithium is the outermost energy level, this electron is called the valence electron. So lithium has 1 valence electron and then 2 electrons contained within the first energy level. The average atomic mass is another piece of information given to us on the periodic table, and it is the weighted average mass of all naturally occurring isotopes of an element. So if we look at lithium, lithium has an average atomic mass of 6.941 atomic mass units, and that means that the average mass of all atoms of lithium is closest to 6.941, which means the most common isotope of lithium has a mass number of 7, since this number is closest whole number is 7. So the atom below this box that would be placed on the periodic table is the most abundant isotope of lithium. It has 4 neutrons and 3 protons for a mass number of 7, and it has 2 electrons in the first energy level and 1 electron in the second energy level. So this would be the most abundant isotope of lithium. And then finally, the oxidation states of an element represent the charge of an ion of an element after electrons are gained or lost. So lithium has an oxidation state of +1, and that's due to the fact that it, when reacting with oxygen, will lose this outer electron and gain a +1 charge. So that's basic information on the development of the periodic table and the information contained within the periodic table. In future lessons, we'll talk about more information that's given to us, including the atomic radius of atoms, their electronegativity, and their ionization energies. And we'll consider the trends of these properties as we look across the table and then down the table. Stay tuned for the next episode, and see you in class.